So yesterday's class had to be ended abruptly because we ran out of time. We were talking about neutralization reactions, which are reactions between acids and bases to form water and salt, and the formation of water is the highlight. And so an example is hydrochloric acid, which is a strong acid, and that being mixed in with sodium hydroxide, which is a strong alkali, to get sodium chloride, which is a salt, and water, right, which tells us neutralization has happened. By the way, in fact,
Yeah.
let me write out the ionic equation for this thing, and then I'll tell you the by the way. So, right, we can write this out normally as we have, or we can write it out with the ions clearly showing. So that and Na plus, so that's also aqueous, and OH minus also aqueous, giving us NaCl. So you've got Na plus aqueous, Cl minus aqueous plus H2O. So you don't have that in the ionized form, and that is a liquid, obviously. Or you could simply boil. So the ionic equation for the actual ionic equation for neutralization is this. If you boil it down, you've got H plus coming in from the acid plus the hydroxide ion from the alkali, giving you this is what you want, right? So if you ask for the ionic equation for a neutralization reaction, that is what you are going to give.
Okay.
Just a sec. Let me mute my notifications here. All right. Now, right, because this is the focus, what we see over here is, right, these ions, the sodium, the chloride and the sodium ions, even after the reaction, they remain as ions, right? It's only the hydrogen ion and the hydroxide ion that have combined to form water, and so they're no longer in the ionic state. And so these guys, right, they are unchanged. All right, so the Na plus and Cl minus ions are unchanged. You would say, well, no, it was, they're not unchanged because the chloride was with the hydrochloric acid and the sodium was with the sodium hydroxide. No, the compound has changed, yes, but the fact that they were ions before and they're still ions later on, that's why they're unchanged. So the ions are unchanged, right? They haven't taken part in the reaction as such, right? Meaning they haven't formed like the water thing, and so they are called spectator ions. And we know what spectators are, right?
Yeah.
So they're just they're just there for the show.
They just look at what's happening.
Yeah. So they're there for the show, and this is what we're actually interested in, right? Okay. Yeah.
Okay.
And as we mentioned, right, the H plus, right, is the ion that causes the acidity. And the OH minus is the ion that causes the alkalinity. right? And water is neutral. It is neither acidic nor alkaline.
Okay.
Clear?
Yeah.
Aram?
Yeah,
Okay.
but like I had a question.
Yeah.
Like if an element is like acidic, so that can also be a base or alkali substance.
A substance can act as both an acid and a base. Good question. I was leaving that for later, but since you brought it up, those kind of substances have a name for them, right? If a substance can behave both as a proton acceptor and a proton donor. So I'll put that down over here. As both base, so proton or right H plus acceptor, and acid, which is a proton donor. Donor. So these guys are called amphoteric. And so this is a term we did come across, I guess, earlier, right? Dealing with metals somewhere, I guess, no point in time to find it at the moment. So, right, if there is such a substance, and there are, for example, aluminum oxide and zinc oxide, right? So you have Al2O3, which is aluminium oxide, and ZnO, which is zinc oxide. And depending on the kind of reaction they're taking part in, they can act as either an acid or a base.
And like, can an acid change into base?
An acid cannot change into a base because an acid is an acid because of its own properties, right? So it can't change, right? It's like asking a cat to change into a bird. It's not going to happen.
But both of them can be
Huh?
neutral. But both of them can be neutralized.
Well, yes,
A
and
base.
right, and neutralization only occurs between acid and base. So you can't cause neutralization by adding two bases together or two acids together. That won't work, right? For a neutralization reaction to occur, you need both acid and base. Okay.
Yeah.
Wonderful.
Thank you.
Sure. Okay. Now moving on, right? There is still some stuff that I've left. In fact, you know, let's go like technically saying going back, right? For us, it's only moving forward. So the right there was a chemist, a Scandinavian chemist called Soren Sorensen. Now you don't need to memorize this. Scandinavian. Yeah, chemist named, and this is like the way they write this, Soren Sorensen. No, the other O is not going that way, right? And he uh, developed what is called a pH scale.
which shows how acidic or alkali substances, if I'm not wrong.
right? pH, so the P is lowercase, the H is capital, stands for power of hydrogen. And so the H is capitalized because it's the symbol for hydrogen, right?
Like, but pH is not only of,
Huh?
like, all the elements have a certain pH, no?
No, not elements, right? I mean, elements
Oh,
on their own don't necessarily
substance.
have a pH. Substances have pH. Compounds have pH, right? So power of hydrogen, and this scale goes from 0 to 14. Right now, between 0 and 7, sorry, 0 to 6, right? If the pH of a chemical is between 0 to 6, that would be considered acidic. And the closer to 0 it is, right, the stronger the acid. Remember strength? We talked about strength yesterday,
Yeah.
right? The more it can dissociate into it, right, giving up the proton. So the closer the pH is to 0, the stronger the acid. pH 7 is neutral, so it's neither acidic nor alkaline. And then, right, between 8 to 14 is alkaline, right? And the closer it is to 14, right, the stronger the alkali. All right?
Yes, sir.
Okay. Along with that, you've got a variety of indicators, right? Indicator solutions or indicator materials. So you've got indicators, right? And they test the acidity or alkalinity of a substance, of a chemical, of a solution, right? Some of them only tell whether it's acid or alkali. Right? For example, a thing called litmus paper. So there are two types of litmus papers, right? There's a red litmus paper, and if red litmus paper turns blue when you dip it into a chemical, that means it's an alkali, right? And if you have a blue litmus paper,
And it turns red, then
that's
acid.
that's an acid, right? Now it's not like, oh, you dipped it in alkali, it turned blue, and you dip the same thing into an acid. No, that's not how it
You will
works.
need different
Yeah, so there are
subject.
two types of litmus paper that you have. Okay.
Yes.
or or for example, you have only one type of litmus paper. For example, you've got the blue litmus paper. If you dip it into a chemical and it stays blue, so that means it is either an alkali because it's not changing color, perhaps it's neutral, right? So nothing's happening. And right, if it does change color, that means it's an acid. So it's only telling you whether the thing is acid or alkali. It's not telling you how strong that chemical is in terms of being an acid or alkali. Okay.
Um, I have a question.
Yeah.
If 0 to 6 is acidic and 8 to 14 is alkaline, then what's 7?
It's neutral. Oh, I didn't
Okay.
write the number here. pH 7. pH 7 is neutral.
Okay.
Right? So as you mentioned, right, water is neutral. Water's pH is pretty much 7, right? 6.8, 7, something like that. The water that you drink, right, is almost neutral, right? Maybe sometimes there was a fad going around, I don't know if it's still around, drinking alkaline water, so it's slightly alkaline, it's like pH 8 or something, 7.5, 7.8, pH 8. For some reason, I don't know why you would want to drink alkaline water, but it was a fad, right? Because water is neutral, it is
Yeah.
naturally neutral. That's what you use anyway.
Okay.
Then there are other sorts of indicators that, right? Acha,
The rainwater is also neutral
rainwater is not neutral
because
because there are
it's
other chemicals mixed into it, right? So perhaps it has sulfurous acid or nitrous acid with it because of the gases in the air and the pollution. So it's probably more on the acidic side, right? And that's not because of the water itself. It is because of the other gases that have dissolved in the water, giving it the acidic property. Okay, so right, litmus paper is an example. There are other liquid indicators that also only change color, right? For example, you've got you know meth, uh, methyl orange and thymophthalene, right? So all of these, there's a table given in your book which tells you how they change color between acids and alkalis, right? Then there's something called universal indicators.
like there are different indicators for vegetables or like the same one
Not for
can be
vegetables,
used
right?
for everything.
There are different indicators depending on the kind of reaction you're doing, right?
Okay.
So, right, one indicator might not be suitable for a certain reaction, the other one, and so you have to choose which indicator you want to use, right? That is a possibility. So it's not like, oh, vegetables this indicator, fruits that, meat that, smoothie and milkshake that.
But everything has a pH now.
Yes, chemically, right? They do have different pH. Or to be more specific, right? Everything has chemicals that have, right? Which chemical, it depends on if like, we talked about citrus fruits, so they might have alkali, right? You can look that up, but right, it's the acid that really shines, the citric acid, so they've got more of that, or perhaps they only have citric acid. So, right, we say, oh, this is like, you won't say the fruit is acidic. The fruit has citric acid. That's what you would say.
Okay.
Okay. Now, the universal indicator, what it does, right, how it's different, is that it has a range of colors, right, going from deep red to all the way to deep purple. And the deep red is like pH 0, so the strongest acid perhaps you can get, and deep purple is for pH 14, so right, a strong alkali. And then everything in between, going from yellow and green and blue and all of that, right? And so when you add these to a chemical, right, they give you a particular color, right? And that particular color corresponds to a specific pH. And how do you figure that out? Right? You look at the chart. So whatever pH whatever indicator you're using would have a chart along with it, or you can look it up online, and you match the color of your chemical after adding the indicator, do the chart and figure out, oh, this is the pH. Another way of doing it is by using a pH electrode, right? So that's an electronic device. Right, so it's an electronic device. Right, and then you dip the electrode into the solution, and it will give you a pH reading on the screen. Okay.
Yeah.
All right. If all of that is clear, we can move forward.
Like, but how are these indicators made, and
Huh?
like how are these indicators made, and like
Uh, that is something I will have to look up, and I don't have an answer for that at the moment. Uh, right, so we can put it as a side quest. You can look it up as well. It is not part of the syllabus, just to be clear on that. So, right, you can try looking it up as well. If I remember after class over the weekend, I'll try looking it up as well, and then we can talk about it next time. Okay. All right. Next up, formation of salts. Right. So we saw in the neutralization reaction that you mixed hydrochloric acid and sodium hydroxide, and you got sodium chloride, right? And so, right, one of the products of a neutralization reaction is a product. So when you use the term salt, it is a product of a neutralization reaction. So a reaction between an acid and a base. Right, so to be more specific, a salt is a substance or a compound uh, in which all the hydrogen ions right, so that's the H plus, have been replaced by a metal, right, by metal ions. And so it said yesterday that we notice acids, right, are, they're mostly, or all of them are non-metals, right, and the bases are metals. So we're basically reacting those two, and so the hydrogen is removed. You've got the metal going in there, right, just like with sodium chloride, right? Sodium is a metal, it's coming in with the chloride, the hydrogen's removed, and you're getting a salt. Right? Or by ammonium ion. So that's something we'll come across later. Ammonium ions, those guys look like this, NH4 plus. Now, salts are classified by whether they're soluble or not. So can be soluble, so they dissolve in water, or insoluble. They won't dissolve in water. right? And so, right, generally for salts, this is how the solubility works. All sodium, potassium, and ammonium salts are soluble. So if you've got a salt that has sodium or potassium or ammonium, it's going to dissolve in water. All nitrates are soluble. All nitrates meaning having this guy. Right, that is the anion that is coming from the whatchamacallit, the acid. So all nitrates are soluble. All chlorides are soluble. So we've come across chlorides, right? The Cl minus are soluble. And when they talk about all, that means, right, any metal that goes with them. So any metal that goes with a nitrate, right, it's going to be soluble. Any metal that goes with a chloride, it's going to be soluble, except lead and silver. So lead chloride, right, PbCl2 if I'm not mistaken, and silver. So that's AgCl2 again if I'm not mistaken. So these two guys are insoluble. Right? All sulfates are soluble. Right? That's this guy. Except barium sulfate, right? So BaSO4, calcium sulfate, CaSO4, and lead sulfate, PbSO4. These three guys not soluble, insoluble. And then you've got all carbonates and hydroxides. All carbonates. So that is the CO3 2 minus. And hydroxides. That is the OH minus. Are insoluble. Except, so they're insoluble. Except, as we talked about here, these guys, all of their salts are soluble. And so you've got sodium. Right, so sodium carbonate would be Na2CO3 and NaOH for the hydroxide. Potassium, right, which would give you K2CO3 and KOH. And ammonium, which would give you NH4 2CO3 and NH4OH for the hydroxide. Okay. So these guys are soluble. Why are they soluble? Because all of their salts are soluble. And right, this is something that you just have to digest. Okay, fine. This is it. Right, this is how it is. Okay.
Okay.
So, right, how do you get carbonates? You get carbonates from carbonic acid. Right, H2CO3. You get, and similarly, right, so that's an example. I'm not going to list all of them. They're in your text. You can take a look at the table in your text. So they give carbonates, ethanoates, chlorides, nitrates, and sulfates, right? And obviously, so ethanoates, since carbonates come from carbonic acid, ethanoates come from ethanoic acid, which we came across yesterday as a weak acid. You have chlorides coming from hydrochloric acid, nitrates coming from nitric acid, and sulfates coming from sulfuric acid. Okay.
Okay.
Yeah.
Okay. Then they talk about different types of oxides. Right. So an oxide is one that has the oxide ion with it. Right. So the O2 minus. Right. So non-metallic oxides and carbon dioxide are acidic. Such as SO2 and carbon dioxide, CO2. These guys are acidic. So not surprising, acids are made from non-metals, so non-metallic oxide is also acidic, right? Which means that, right, when you add them to an aqueous, right, an aqueous solution of these guys, if you dissolve them in water,
Like, aren't these harmful for us because we inhale or exhale carbon dioxide?
I'm sorry, could you repeat that?
Like, aren't these harmful for us?
Aren't these?
Harmful for us? Like, they
Uh,
are.
I mean, yes, right, probably, depending on how you are interacting with them. Like carbon dioxide is not harmful in the quantity that's present in the air, right? It's the percentage is there, it's very low. In fact, it also helps in the gas exchange, uh, right? And there is, right, so we think that when we're breathing, all of the carbon dioxide leaves the body, 100%. No, in fact, if you study it in detail, this is something you'll probably come to know if you take up biology in A level. There's actually a very small percentage of carbon dioxide that is removed from the blood in the body, and there's a lot of carbon dioxide that sticks around. So it's harmful depending on how much there is, right? Some chemicals are harmful even if there's a little of them in the body, right? And then others, right, depends on when maybe the body can take a bit more. If you're talking about them falling on your skin, then again it depends on whether it's a strong acid or a weak acid, or strong alkali or a weak alkali, and how much of it and for how long. right? So all of that depends. But in general, if you know you're dealing with this kind of substance, right, you might want to wear protective clothing and protective gear like gloves, right? That doesn't mean you wear gloves and like goggles when you're having like an orange, right? You probably don't need that, but right, with more harmful chemicals perhaps,
Okay.
right? So for example, a chemical that can cause harm to your skin is bleach, right? Because that has a very high concentration of ammonium, right? Ammonium hydroxide or ammonium salts. And so, right, if you're working with bleach and if you have if some of it touches your skin or spills on you, you would want to wash it off with a lot of water, running water, very quickly. You don't want to leave it lying around. Otherwise, it will cause the minimum it would do is cause irritation, and right, it could be worse.
Yeah.
Okay. So, right, when you dissolve these guys in water, you make an aqueous solution, they will produce hydrogen ions, right? And that is the whole point. There, that has okay. They're acid. Metal oxides are bases, right, or basic. And so, if these guys are dissolved in water, you make an aqueous solution of them. And so, they will produce hydroxide ions. Right? And so, an example of this is, for example, calcium oxide, right, or copper 2 oxide. Then the third type of oxides, which are rare, are amphoteric oxides. Right, and so these can act as both acids and alkalis. To produce salts, depending on what you're reacting them with. And again, right, we gave the example of zinc oxide and aluminium oxide. Both of those are valid, aluminum and aluminium. Do we have time? We have time. So let's keep going.
Oh my god.
Huh?
Yeah, let's keep going.
Ah, I'm guessing you're tiring out. There's
Kind of.
a lot of information coming your way.
Yeah.
How do you feel, Haram?
Same.
Same? You want to stop here?
It's your choice. Like,
Well, it is, but the thing is that if you're feeling that there's too much information, there's no point in me going. I mean, if you're not able to take it in. Otherwise, I can keep going. You're going to zone out, but you can, take a look at the recording later on to digest the rest of it. What would you prefer?
honestly, it is interesting, so we can keep going.
Okay, so be it. That's two against one.
Yeah, sure.
Okay, right. So next up is methods of repairing soluble salts. And so for this, right, there are 4 methods to do this, right? You all of them involve reacting an acid with, either you reacted with an excess of metal, or right, you reacted with an excess of insoluble carbonate, the third is reacting it with an excess of insoluble base, and the fourth is reacting with an alkali, right, by a process called titration. Now, 2 things over here. First of all, why are they using excess, right? So that all the hydrogen ions being given up are reacted, right? So you have a complete reaction. And so whatever you have left up of the metal or the insoluble carbonate, as we will see, that will not react because it's more than what the acid can handle, and right, it will settle at the bottom or something. And the second, right, what's the difference between a base and alkali? Right, so we've been using those terms interchangeably, right? And to, the book defines that as well. Alkalis are soluble bases. So if you got a base that is in powder form or something, and right, you mix it into water, you dissolve it in water, it does dissolve, it does form a solution, it is soluble, then that soluble form of the base is called an alkali, right?
Yeah.
And right, as you know, aqueous solutions that we just talked about of alkalis contain the hydroxide ion. All right. So these 2 things to keep in mind as we go on. So first up is the reaction of an acid with excess of metal.
Like, aren't salt found like naturally in the environment just like base and acids?
Salts are found
Yeah.
naturally, yes, because some sort of reaction at some point has taken place. Right now, keep in mind when we use the term salt, we're talking about like chemically it is a salt, means some reaction has taken place between something that was an acid and something that was a base or an alkali. We're not talking about the salt that we use in cooking.
Yeah. Like
Okay, that is also a salt because we just saw hydrochloric acid reacting with sodium hydroxide will give you sodium chloride, which is the salt we use in cooking, right? But the common term salt used for sodium chloride and the chemical term salt using for any compound formed as a result of a reaction between acid and alkali, we just need to keep that in mind. And yes, salts are found naturally because reactions are taking place, all the time. Okay, so what are we going to get? What is the general reaction that's happening? You got an acid, you add some metal to it, you will get a salt, and you will get hydrogen gas. Right? And so we generally use less reactive metals for this. And so they've given you sort of an acronym over here. The ones that are usually used for this method of salt preparation, you can maybe remember them this way. So that's magnesium. Can you guess which these are? What's the A?
Aluminium,
Aluminium.
zinc,
I believe Sophia is switched off. Zinc.
Yeah,
Then,
I have signed out for the day.
yeah, iron, and T is for tin. Okay. So what you do is, for example, you take dilute hydrochloric acid. Again, dilute does not mean it's weak. That just means there's less of the acid and more of the water. Right?
yeah,
You take dilute hydrochloric acid, right? And you add excess of magnesium ribbon. What's magnesium ribbon? It's magnesium in the form of a ribbon. Remember, metals are malleable.
like in a form of ribbon.
Yeah. So basically, strands of magnesium, something like this. Magnesium in this, like it's been processed to look like that. You don't take a lump and you just like throw it in there. You don't do that. Right? And so why we're using excess, we already mentioned that all of the acid reacts, right? All of the acid reacts. So we want a complete reaction. Right? And so we will have some magnesium, unreacted magnesium left at the end. And right, in this reaction, you will observe effervescence. Effervescence. Right? And that is, you will notice a bubbling and production of gas. And in this case, what you're getting is hydrogen gas. So the complete reaction is HCl, which is aqueous, plus magnesium, which is solid. You're getting MgCl 2 plus, so that's aqueous as well, plus H2, which is a gas. Haram, would you like to balance this?
Yeah, like they are already balanced. Like they have to add two hydrogens to the reactant side. One more hydrogen to the reactant side.
The reactant side. So we put 2 over here. So now you've
Yeah,
got 2 hydrogens and 2 chlorides.
yeah,
You've got 2 chlorides and 2 hydrogens, 1 magnesium, and it is balanced. Right? So you're getting this soluble salt because that is the whole thing we're doing, methods of preparing soluble salts. Right? So it is aqueous and hydrogen gas is being released. Now, what is happening to the hydrogen gas? Right? HCl basically means you've got this, right? And so what's happening is in this reaction, magnesium is going from an oxidation of state of 0 to an oxidation state of +2. And hydrogen is going to 0. And so if you write that out separately, what's happening is that the hydrogen is receiving, because 2 plus means it has lost 2 electrons. So hydrogen is receiving electrons from magnesium, right? And so you've got 2 hydrogen receiving 2 electrons from magnesium going to H2. That is the ionic equation. Okay. Now, how do we finally, just to wrap up, how do we process this and get the salt that we want? Well, first of all, right, let me go to the next page, right? So you remove the excess magnesium by filtration. So that is an experimental technique. You take a funnel, right? You pour the liquid in. Let me just, right? You take a funnel, you pour the liquid in. There is a filter paper over here, right? That allows the liquid to pass through. You collect the liquid, and right, the magnesium, which is solid, will be stopped by the filter paper over here. So that's how you're separating it, right? So you filter it to remove the excess magnesium, right? And you evaporate. So basically you are removing the water, right? Evaporate and concentrate or make a saturated solution of magnesium chloride. Then, right, you dip a cold glass rod into the hot solution, right? That solution is a magnesium chloride, MgCl2 solution. And if, right, salt crystals form at the end of the glass rod that you've dipped in, the cold glass rod, then the solution is ready to crystallize. Ready to crystallize. Right? So it is left to cool, right? And crystals of the salt form. So then they are filtered again. and dried between clean tissue papers. And that's it. So now you have your soluble salt. Keep in mind, having a soluble salt does not mean it will always be in aqueous solution.
Like, do we use these soluble salts in our real life, in like our daily life use?
Sodium chloride.
We obviously do use sodium chloride, I guess.
Huh?
We do use sodium chloride.
Exactly.
Like,
That's again
asking about this salt.
magnesium chloride.
Yeah.
I don't think we do. Right. So magnesium chloride can be used in health products, right? So it's not something that you would normally use, but as food supplements or tablets or capsules, right? But again, as you asked, it's not something that we regularly use on an everyday basis. Okay, the class is about to end, right? Thank you. I'll see you guys next time. If there are any questions, you can put it on WhatsApp, and do review the chapter and have a good weekend.
Allah Hafiz.
Allah Hafiz.
Allah.